Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields, and strengthen ties between Michigan State University and the community. Today we have the pleasure of presenting a public lecture by Professor Katja Nowack from Cornell University entitled Seeing with Magnetic Eyes, From Superconductors to Topological Matter. Professor Nowack received her PhD in physics from Delft University of Technology in 2009, where she studied the control and readout of single electron spins in electrostatically defined quantum dots for spin-based quantum information processing. As a postdoctoral researcher at Stanford University, she shifted her focus to low-temperature magnetic imaging using scanning superconducting quantum interference devices. In 2015, she joined the Department of Physics at Cornell University, where her lab develops advanced magnetic imaging techniques to study quantum materials and devices, including topological materials, unconventional superconductors, and superconducting circuits. Since January 2025, she has served as co-director of the Cornell Center for Materials Research. If you have any questions during this talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Professor Nowack.
Well, thank you very much for the introduction. And yeah, it's my pleasure to be here today and have the opportunity to tell you a little bit about both what's concretely going on in my research lab, and then maybe also more general, higher level, like why is, I think, the research area I'm in interesting and exciting. As Dean just said, if there are questions in between, I actually welcome that and happy to answer them on the fly. And then I also understood there's like a little opportunity for Q&A at the end of this. I'll try to keep it at about 45 minutes. So we'll have some time to talk afterwards. All right. So should have tried if I can. Here we go. So this is my plan for this talk. I briefly want to talk about are actually quantum materials. And that's just going to be one short slide, but then I pick superconductors as actually an example as a concrete quantum material. Then I'm going to talk, probably the bulk of my talk is going to be what does my lab actually do to study quantum materials. And then I have a very brief slide at the end, also kind of re-emphasizing why is this kind of research actually important for science and society. All right. So let's get started. What is a quantum material? So first of all, there's no sharp definition of what a quantum material actually is. And so I pull some definition from a paper by Keimer and Moore titled The Physics of Quantum Materials. And how they define it is the following. First, they say the physical description of all materials is rooted in quantum mechanics, which describes how atoms bond and electrons interact at a fundamental level. Although these quantum effects can in many cases be approximated by a classical description at the microscopic level, in recent years there has been growing interest in material systems where quantum effects remain manifest over a wide range of energy and length scales. So here we go. Such quantum materials include superconductors, graphene, topological insulators, and a few other examples. And so how I would summarize that is quantum materials as those that exhibit emergent phenomena on, microscopic length scales potentially, which refers to the collective behavior of many electrons, leading to properties that electrons behaving independently in a material would not have. So for instance, if you take something like silicon or gold, the way we understand the behavior of silicon or gold is actually that we think very much about electrons living in those materials as independent, whereas there's other materials where really that kind of framework breaks down and you really have to think about what the electrons collectively do. I because I wanted a picture on the slide, I gave ChatGPT some prompts to come up with an image. And so this is ChatGPT's idea of electrons behaving collectively in a quantum material. So now this might sound all a little vague and abstract, lots of words, but let's talk about like one prime example of a quantum material, and that is actually a superconductor. So let's talk about what is a superconductor. Well, first of all, a superconductor is a superconductor. And that refers to the fact that a superconductor has zero resistance to electrical current. And this was discovered quite a while ago at this point in 1911 by Kamerlingh Onnes when he measured the resistivity or resistance of mercury down to very low temperatures, and then observed in the resistance this very sharp drop at a temperature of about 4.2 Kelvin. And the resistance here in those papers looks like it's really going to zero. And the reason Kamerlingh Onnes could do this in 1911 is that he was actually the first person that managed to liquefy helium. And liquid helium is a good way to get to very low temperatures. I should say 4 Kelvin. Kelvin is a temperature scale. 4 Kelvin is 4 degrees Celsius. Well, it's 4 degrees. Let's just call it 4 degrees. 4 degrees above absolute zero. Okay, so contrast that with a normal conductor. A normal conductor has non-zero resistance. What that means is that the electrons passing through a conductor, they bump off vibrations of the lattice of the material. They bump off impurities. That gives the electrons resistance against going through the material. And if you have resistance, you have losses, and those losses lead to heating. And so that's why in a normal conductor, if you run enough current, it will actually start to glow. Another property next to zero resistance that a superconductor has, and that's more subtle, is that a superconductor will expel any magnetic field applied to it. And so that is actually, maybe you've seen this before, like this image of like a little magnetic cube levitating above a piece of high temperature superconductor immersed in liquid nitrogen. And that property that it expels magnetic fields is actually a key difference between just a perfect conductor and a superconductor. How do superconductors work? I can't explain it in all details, but I want to give you a sense of what's happening. And so first of all, superconductivity is a quantum state of matter in which electrons behave collectively, so as they should in a quantum material, over length scales that you can see. And just that is something that personally still blows my mind if I say it out loud. And so how does that work? So actually, Bodine, Cooper, and Schrieffer figured out a theory of superconductivity in the late 50s. So here we are back to our normal conductor where electrons go through. The material is made out of metal atoms. The electrons bump into each other, bump into the motion of these metal atoms. Maybe they are impurities. And generally, the electrons repel each other and they scatter, and that leads to this normal resistance. Now, what can happen in a superconductor is, or what does happen in many superconductors, is that at some critical temperature that is low, there is an effective attraction between these electrons created. And here's a way to think about it. So if electron number 1 goes through the crystal and these metal atoms are positively charged and the electron is negatively charged, so as the first electron goes through, it will attract the metal atoms and just lead to a very small deformation of the crystal, leading to kind of a channel where there is enhanced positive charge all of a sudden in the crystal. And that excess of positive charge can be attractive to a second electron, essentially following the first electron. And what you've created is an effective attraction between these electrons. Now, here I have to kind of wave my magic wand, and I can't give you a better explanation, but it turns out that this effective interaction between the electrons can lead to the electrons wanting to pair up. So they start forming what's called a Cooper pair, And it turns out that in quantum mechanics, once the electrons are paired up, they change character and they're allowed to condense. And so these Cooper pairs actually then condense into what we call a macroscopic quantum state. And it's really that quantum state that comes with a collective rigidity that results in zero resistance. I think Schrieffer had this analogy of like thinking about ice skaters linking their arms while they skate over the ice, and because they're paired up and linked to each other, if one skater runs into a scatterer like a bump, like that skater will not fall because it's like there's the rigidity coming from having arms crossed with the other skaters. Maybe an interesting analogy. Okay. So we understood how superconductivity works. We discovered it in 1911. It was understood in the late 50s. So why is it still a research frontier? Turns out that there's unconventional types of superconductors that are still puzzling. And we're also still discovering new materials that superconduct, and we still are learning how to really predict superconducting materials in the first way, how to predict them. And so what are questions? So for instance, if you have a superconductor, sometimes it's actually hard to figure out what glues these electrons pairs together. So the deformation of the lattice was one possibility, but turns out that there's other possibilities that allow these pairs to form. There are questions, can we create and engineer entirely new properties, maybe by finding other ways to create these electron pairs? And then there's a big question on how do you create a superconductor by design? And so those are all really interesting research frontiers. This all said, superconductors to date are actually already super useful. So quantum materials to date can be very useful already. A lot of applications of superconductors make use of zero resistance. And the idea is pretty simple. If you can run a high current, you can generate magnetic fields. And so if you don't have resistance, that makes it easier to run very high currents. And so as such, superconducting wires are actually used as an integral part of magnets. So if you've ever been in an MRI machine, you are actually surrounded by a very cold bath that has a very large superconducting magnet in it, a large solenoid, which is living in that donut. And then also this is an image from, I think it's Commonwealth Fusion Systems, that are building a new type of fusion reactor. And for that, you also need very strong magnetic fields. So you see like a segment of a superconducting magnet that they're actually building. Superconductors can also be very sensitive sensors. So you can use them to sense light and other radiations. The way to understand that is like, well, if you could tune your system, if you have this superconductor with this very sharp resistance drop at a given temperature, if you're anywhere close to that temperature, you can imagine that if your system heats up just a little bit, you can do an electrical measurement to sense that very readily. And so that principle that sensitivity of superconductors is actually already in use, for instance, in big astrophysics experiments. So it turns out that you have, I show a picture of this is actually a rendering that's not there yet, but of the Fred Young submillimeter telescope that's under construction by a collaboration that's led by Cornell, CCAT, and it's going to be in the Atacama Desert in Chile. There are already a number of telescopes up there. And at the heart of these telescopes are actually superconducting detector arrays. They cool them down to about 100 millikelvin at 5,600 meters elevation, and use this high sensitivity of superconductors to sense, for example, the cosmic microwave background. All right. If you introduce what's called a Josephson junction, which is kind of a nonlinear element, much like a transistor for electrical circuits. So if you introduce a a Josephson junction as a circuit element. And what that is essentially a little sandwich of a superconductor, then an insulating layer, and then a superconductor. You can build superconducting circuits. One superconducting circuit that's very relevant to me is what's called a superconducting quantum interference device, or a SQUID. It turns out that these are very sensitive magnetic field detectors. Here's a little circuit diagram. The details are not too important, but you should see that there's a big loop that's actually superconducting. You have two of these Josephson junctions in it. And all you need to know about this device is that if you do an electrical measurement, so let's say you run a current through it and then you probe the voltage, the answer that you get from that electrical measurement is very sensitive to the amount of magnetic flux that threads the loop. And so that is what it makes it a magnetic field detector. Turns out that these are used in quite a few ways. One is, again, in the medical field, actually. There is an interesting technique where you essentially have this kind of helmet, and if your head goes into this helmet, you should realize like you're only like probably a centimeter away from 4 degrees above absolute zero, because what's living on the inside of this helmet is an array of these superconducting quantum interference devices. And for them to work, they need to be superconducting, and so they need to be cooled to sufficiently low temperatures. But what they can do is they can measure the magnetic fields that are produced by the electrical currents that are running in your brain. And they can do that at pretty high temporal or time resolution. Turns out that SQUIDs are also very dear to my heart. So that is actually the kind of sensor that we use in my lab to image magnetic fields. And I talk quite a bit more about that in just a moment. One point that I like to make in this kind of talk is that I said a few times you need low temperatures, but superconductors, and you might think, well, this is difficult to achieve. That sounds like it's not useful for anything, but superconductors are technologically useful even if they require low temperatures. Of course, there's also efforts to create superconductors that superconduct at much higher temperatures, but even the ones that do superconduct at low temperatures are technologically useful. And one part of this is that there has been a lot of progress in cryogenic cooling. So these kind of instruments are still used to date, of course, but this is like how I spent my PhD. Now, I didn't put where this picture was. It may have been in Pittsburgh. I should have put the reference. This is not exactly the system that I used in my PhD. It's from somebody else's lab, but it's the very same, Oxford Kelvinot's 400 system. And so you immerse like this long stick right here, which carries your experiment at the very bottom. You essentially dunk it into a big bucket filled with liquid helium. There's good reasons why you might want to do that still to date. There's very low vibrations in these kind of systems. But that was, the choice that we had about 20 years ago. At this point, you can buy cryostats that are walk-in closets. So like Blueforce has brought out, I don't use this in my research, but in principle, there's like cryostats that go just as low in temperature that are essentially functioning as a walk-in closet. There's no liquid helium involved anymore. It works with cryocoolers. There's, of course, some cooling power or like electrical power that you have to provide. But it's gotten a lot easier in this way. And so this I think advances in cryogenics also fuels potentially future uses of superconductors. And so one big future use of superconductors might very well be in tomorrow's computers. I think here both about classical computing as well quantum computing that you may have heard about. I won't talk about quantum computing really, but there is a way to do quantum computing with superconducting devices. And that is maybe becoming a reality is kind of like emphasized by a lot of companies actually investing in this technology. These are all kinds of like really big companies, also kind of smaller startup companies that are all working on realizing quantum computing with superconducting devices. And there's also some companies here that are pushing classical computing using superconducting devices. And SNOWCAP here I actually made really big because I like their logo, or their slogan, I should say, which is the next chapter of compute begins below zero. Of course, this is not going to be in your laptop. You won't carry this around with you, but this might very well be how your future data center actually looks like. All right. So now switching to what does my lab actually do? I already gave you a brief flavor, or does anybody have a question in the meantime? Maybe not. It's not. No, okay, then I just keep going. So what does my lab actually do? So we use these squids that I just introduced you to already to image magnetic fields. And I just saw that Martin Huber is actually on the webinar. And I still today, maybe I should update this picture eventually because it's an optical image of a squid that was made, maybe, if I had to guess, some not quite 20, but like maybe 17 years ago or so. And I still really like this optical image. And so this was a squid actually fabricated by Martin Huber at CU Denver. And so this is a relatively large chip, but the really important part of it is kind of like the front part here, which has a small superconducting loop. If you look closely on the zoom in here, there's a loop. We call this loop the pickup loop. And that is the one that does the magnetic sensing. So these sensors do sense the magnetic field that threads this small loop, which is more on the micrometer scale. So for reference, your hair is probably somewhere around 40 micrometers thick. Make that 40 times thinner, and then you have about the dimension of this pickup loop. And then there's also this field coil that also has a job to do in a lot of our experiments. I might briefly explain that later, but maybe also glance over it. But so this gives you an idea of how small an area we can sense the field. And so what we do in my lab is we take these kind of sensors, we mount them on a set of motion stages, and this is and then we scan this loop pixel by pixel by pixel over a sample or a piece of material to create really images of the magnetic field coming out of that sample. And we do that at low temperature. So now I'll just give you a feeling for like how the instrumentation in our lab might look like. So we do this inside a cryostat, and here you have a kind of like a cut drawing or a design drawing of one of our instruments. That's the refrigerator, and our experiment actually, or our microscope, lives down here at the bottom, so I can zoom in. This is kind of a sliced open design drawing of our microscope. There's a lot of stuff going on, but all these pieces, this piece, these pieces, and even these gray slabs, they are all for moving the squid around. So those are our scanners. And then it's really up here, if I zoom in, where the squid sits, and the sample is mounted upside down. We bring the squid very close to the sample, raster it around, and get an image. And in this specific experiment or instrument, we can go to very low temperatures while doing that. So my kids like this probably the most. So the summary of what we do in my lab is we have a squid sitting in the cold, and it looks at magnetic stuff. You might notice it says Molar Lab. This is a drawing that we actually had made by Derek Jr. He has a beautiful children book, Sit the Squid. So he made this actually for us while I was still a postdoc in the Molar Lab at Stanford. Yeah. Okay, so now you could ask, okay, great, you have this technique. Why do you like it? So why do you need magnetic eyes to study the physics of quantum materials? I give a very high-level argument that's very simple. Well, if you think about what's going on in a material, magnetic moments and moving charges are at the heart of many of these collective phenomena that we find exciting. And it turns out both magnetic moments and also moving electrons generate magnetic fields. And so then you can make a simple argument. If we can measure these magnetic fields generated by magnetic moments and moving charges, we'll get a pretty nice window into what's going on in our material. And so in the kind of second half of the talk that we're hitting now, I'll give you just a few research nuggets of how we use this technique to see different phenomena in quantum materials. And so we study, what else drew me into this technique is that we study actually quite a few different phenomena. So for instance, we study flux trapping in superconducting circuits. I'll tell you more about that in a little bit. We do also a little bit of work on these unconventional superconductors that we don't understand very well yet. We do work on superconducting sensors of the kind that go on these telescopes with a hope to make them better. We've had work where we study, say, how can we control with strain superconductivity in some materials. We use this technique to also image currents, and I'll tell you more about that. We study dynamics in model systems. And then next to these activities, we also try to develop new magnetic imaging tools as well. All right. From these, I'll talk a little bit more about these 4 topics. If we're running out of time, I might skip one of them, but here we go. Let's start with where do we start? The superconducting transition in sensors. All right. So I already told you a little bit about this, but they're so-called transition edge sensors that make use of that very sharp superconducting transition in a superconducting structure when you measure resistance as a function of temperature. And so if you position your system right here, right on the transition, then what you're actually building is an incredibly sensitive thermometer. So you keep monitoring the resistance. If your temperature changes by delta T, either it goes up a little or it goes down a little, you see a big change in the resistance. And so that's how you build a thermometer. How these type of devices, I already said this is used in astrophysics. So what might provide, for instance, a little bit of heat to change the temperature is a photon or some radiation falling on your sensor. All right, so how does this kind of device look like? Well, this color of purple is essentially the substrate. Then you have a superconducting lead to this device. And in this case, it's made out of molybdenum, which has the superconducting transition at about 1 Kelvin. And then there's like a weaker superconductor sandwiched in between the leads. In this case, it's a molybdenum gold bilayer, and that has a much lower critical temperature. So it's a superconductor structure. Only the 2 involved superconductors have different critical temperatures. And so these are used, again, I'm showing some images of telescopes here. These are already the pixels and cameras that are actually actively used on a variety of telescopes. These are not even all the telescopes that use these kind of superconducting arrays. And they're also the target or sensor of choice for some planned missions like the Athena X-ray observatory that may launch in more than a decade from now. And in this case, these TESs would not, like in these telescopes, they detect the cosmic microwave background. For this kind of mission, you have to optimize TESs that actually detect X-ray radiation, which they can do too. There are some challenges and opportunities with these sensors. A deeper understanding of the superconducting transition, like exactly how does that shape actually look like, is needed. Or if you have that understanding, you can really improve the performance of these sensors. And the approach to date to understand the superconducting transition is just a lot of electrical characterization. So you measure a lot of them, and then you do modeling. And it turns out that with our imaging technique, we can actually directly locally see what's going on in these devices. So that's nice. So here's again the devices that I just explained. And now I'm just showing you images that are taken with our imaging technique of how this device actually goes superconducting. So at relatively high temperature, which is 100 thousands above absolute zero. So here I call this high temperature. It's the leads of the structure are superconducting, and so that shows in these images as a dark color, and then yellow is like nothing, like no superconductivity. And then I can go down in temperature gradually. So I go here, here, then here, then here, then here, and so on. And I can really gradually see this whole device. In this device, I can see the superconductivity turn on. And so there's a lot of information on how the superconducting transition in these devices really happens. And we can kind of compile this kind of image series and some additional information. But our hope is really by doing this kind of work that we understand the superconductivity in the sensors better, and with that improved understanding to improve their performance. So that's actually a very active, ongoing project in my lab. Another nugget that I have is we work on flux trapping in superconducting circuits. So let me tell you a little bit about that. So there is a vision. This is work that I do or my lab does in collaboration with IMEC. IMEC is an R&D organization in Belgium, but they also have parts in the United States, among others, the kind of test and design group that works on these superconducting digital circuits. And here is kind of a blueprint of an architecture that should realize, based on superconducting devices, a very energy efficient computing, and that's specifically in support of AI. There's some more details in the schematics on how the logic actually works. Maybe the most important thing to point out here is that it's all based on superconducting wires and Josephson junctions again. Okay. There's one challenge in this technology, and that is that thin film superconductors, I told you superconductors expel magnetic field, but that's not strictly true, certainly not in thin films. Actually, if you apply some field, the magnetic field can enter in the form of vortices. So these are like little, maybe like pinholes almost, that form in your superconductor, not a physical hole in the material, but a hole in the superconductivity where kind of the magnetic field all of a sudden rushes through. And so those are superconducting vortices. They're really kind of like the magnetic field kind of comes through in this hole in the superconductor, and around this hole there's like really big swirling currents flowing. And we can image these things. So like now I'm playing a little movie of just an image that we took. It's about 200 by 200 micrometer. It's on a thin film superconductor, and what you see wiggling around are essentially vortices that are trapped in this superconductor. And so each bright dot essentially is a bright dot of magnetic field. And we see them this way because of these swirling currents. The swirling currents going around the hole generate magnetic field, giving us a bright dot in our imaging. And so the vortices are actually a challenge. So if in these large superconducting circuits, if a vortex gets trapped in a place that's not controlled, because it generates this magnetic field, it can couple magnetic flux into the circuit where it's undesired. And if there's too much magnetic flux coupled into parts of the circuit where they don't want it, it leads to a failure in their logic. And so, so they need to really understand and control where these vortices actually end up in the thin films. And so this is kind of work that we can try to support. So one way to control where the vortices are, you make artificial structures. And so it turns out that we actually, if you punch an actual physical hole in the whole film, that if a vortex gets created in your film, it's energetically beneficial for the vortex to hang out in that hole. There's some competition with defects in the natural film this is made from. And so the kind of work that we do is answering questions like, how big a hole do I have to make, and how closely do they need to be spaced, so that that these artificial structures successfully trap all the spontaneously forming vortices that you might have in your film. And so these are images that we can take. So here I show images of these artificial structures where on this axis, the spacing between the holes varies. And along this axis, the holes get bigger. And so we can see that, yay, at a certain combination of spacing on the hole size, things work fine. Green means great, it worked. Whereas if the holes get smaller or they get more spaced out, these artificial trapping structures actually stop working. Okay, so that's one kind of project that we do. Another kind of recurring theme is that sometimes instead of dealing with real materials in this research area, it's nice to study so-called model systems or artificial materials. And so one artificial model system that you can make of to study again, superconducting dynamics or dynamics of vortices and phase fluctuations in superconductors is you just make an artificial superconductor, which in this case is a Josephson junction array. There's a lot of superconductor in here, but and actually this picture throws me off sometimes still, because it's like there's an optical illusion in this picture. What this is, it's a scanning electron microscopy image of an array that my postdoc Shishun Lee actually made. And what you see, it's gold. The light gray is gold, and on top of the gold is actually the dark structures are on top of the gold are these crosses. And there's little gaps in between the crosses. And so at the gaps, you have superconductor, then you have gold, and then you have superconductor. And it turns out that that also makes a Josephson junction. So we have a periodic array of Josephson junctions kind of arranged in this square lattice. If you trap a vortex in this kind of artificial superconducting structure, it's going to be a circulating current that goes actually around this little plaquette that you made. So it will cross 4 of the Josephson junctions and just have a current going around. And this is a zoom in of the Josephson junction. And so if we just have this array and trap a single vortex, this is how it might look. Like in the magnetic image that we take of an individual vortex, just gives us, now the vortex is actually dark in color, gives us this blob right at this plaquette. If we can control the number of vortices in the structure by just applying a little bit of fear to the structure. So if we apply enough fear that about half of these plaquettes want to trap a vortex, then we get a pretty image like this, where you get this checkerboard pattern. But we can play that game also. So that's what we call filling 1/2. So that means that we apply enough field that 1 out of 2 plaquettes trap a vortex. And then we can, of course, also go to other fractions and really discover these very beautiful kind of vortex lattices and regular arrangements happening. And these regular lattices form because vortices actually interact with each other. So they're a result of vortex-vortex interactions that drive them to form these very periodic structures. And so this is quite beautiful. We can also see how these lattices melt either by increasing temperature or maybe by going away from just like this very perfect rational fraction of 1/3 or 1/2. And then finally, we can also see how it melts. I don't show that here as we start applying currents. And so we're having a lot of fun, really understanding very fundamental kind of vortex physics by imaging these Josephson junction arrays. So these were all superconducting examples. It turns out we do, at this point in time, do a lot of work on superconductivity. I'll finish with one kind of little highlight on a slightly different topic. So this is on a topological system. And in this system, we actually use magnetic imaging to image how does the current actually flow. So let me first motivate why this might actually be an interesting question, like asking the question, how does the current actually flow in a device or in a material? So if we make a new material or if we study materials, often what happens, at least if they are materials that can carry a current, is we do a transport measurement. And so a transport measurement, how does that look like? You make a device that might look like this. So in gray, you pattern the whole bar. you attach metallic electrodes to that hole bar. So this is like your material of interest. This is just like some metal that makes a good contact to the material of interest. And then you apply a bias voltage across the long channel of your device. So a current will start to flow through the channel. And then typically you just measure voltages. So you might measure what we call the longitudinal voltage between these two electrodes right here, Vxx, that informs you about just the resistance of the material. And if there is a magnetic field applied, or maybe your material is magnetic, you might also get what we call the transverse voltage. So like a finite voltage drop between these two opposing electrodes that are perpendicular to the direction of current flow. So we call this Vxy. And then one way to think of your material, though, is like maybe you could think of this whole piece of material as consisting of like a teeny tiny resistor network, just like this. So you kind of decompose your like electrically to think about a material. This would be a valid way. And it turns out if you give all these values of this resistor network, and you say what amount of bias voltage you're going to apply, you can actually predict what's going to be the outcome of this transport measurement. You can predict what Vxx and Vxy you're going to be measuring. You can also, if you have all these resistor network values, you can also compute how the local currents and the local voltages actually are going to look like. However, it's important to point out that the inverse is not true. Like if we actually do what we do in the lab and we do this transport measurement, right, we get four numbers. We know the bias voltage, we know the current, we know Vxy, we know Vxx. But it is in principle impossible to reconstruct all these local resistor values. We can't reconstruct how the current is really flowing inside the device and what the local voltages are doing. And so the piece that I want to draw attention to is like what we actually do when we do this transport measurement in the lab is we typically just assume that all these resistors are the same. So when we do a transport measurement in the lab, we very often interpret it under the assumption that this material, the underlying material, is extremely uniform. And it turns out oftentimes, especially when you work on new materials, that's not a good assumption. Sometimes it's not a good assumption because the material itself might not be very uniform. Sometimes it's also not a good assumption because of the underlying or physics that takes place. And so that's a motivation for, maybe in some materials, you actually want to do imaging to really understand how the local currents actually flow. And so it turns out magnetic imaging is a good way to do that. That's relatively straightforward to explain. We can image currents by measuring the magnetic field. So if you have a current flowing in a sample, let's say here the current flows actually along the edge or through a single wire, that current will generate a magnetic field, and then you can come in, measure very carefully that magnetic field, and typically we measure just one component. But it turns out that by measuring just one component of that magnetic field, you can reconstruct how the underlying current was flowing. At least this is true if the conductor you're looking at is two-dimensional. If it's a true three-dimensional conductor, you can learn something about the current flow in your sample, but it gets a little bit more involved. And so the type of sample where we've most recently done this is what's called a quantum anomalous Hall insulator. And so really don't have much time to explain what that is. It's a topological state of matter. It's very interesting. I think in another edition of this talk, I would also introduce you to the quantum Hall state. So you had like my mind blown with the superconductivity quantum Hall, and quantum anomalous Hall is like the second type of effect in condensed matter that still blows my mind when I talk about it. It's like this effect that you can have different shapes of samples, different types of disorder and non-uniformities in your sample, but nevertheless, if you do an electrical measurement on your sample, you get the measurements of this transverse voltage or transverse resistance then that is extremely quantized, not just, and like it comes out to a value h/e squared, which are two natural constants, and it comes out to that with very, very high precision, and that's due to topology. I'll leave it at that. I will say that we decided to image currents in this material, and we perfectly knew what we were going to see, because the literature, if you ask the literature of how does the transport current actually flow in this material, it talks about so-called F states. So the current was going to flow along the edges. And one paper after the other, if you read them, say edge conduction, chiral edge conduction is one-dimensional, and so forth. So there's a strong consensus in the literature. The transport current is going to flow along the edges. And so there's a specific type of material that we studied coming from Penn State to us, and my former graduate student, now postdoc at the Max Planck Institute in Dresden, actually already since 2 years, 3 years maybe even, has done these experiments. I'll rush through them and get to the punchline. We actually found that the current does not flow along the edges in these materials. So it became a very interesting, worthwhile experiment. And what we see instead is that the current, so here you have the outline of this Hall bar. Let's say this is the interesting topological material in lighter gray, and this is a metallic contact. Turns out when we look at the current for some reason comes in through a very bunched up corner of this contact up here, and then just spreads uniformly into the sample. And if we if we change a characteristic of the sample, we can actually flip the corner at which the current comes through. Turns out that there is an explanation for this, which kind of takes a different point of view on how this quantized transport comes to life in these materials. Don't have time to go through that. I might leave it at that. Can take a lot of pretty images. I want to come to my last slide, which is just very briefly emphasizing why I think that this kind of research is actually important. So very high level, it's useful to deepen our understanding of collective electron behavior in materials. And I think that's probably going to be important to drive next generation technologies. And there's some things that are on the near horizon, right? There might be new versions of computing through multiple approaches involving superconductors, maybe also other types of materials. We might be able to build better detectors and sensors for various fields. But a lot of this research is definitely also blue sky directions. It's like very curiosity driven and blue sky. Such as like searching for new pairing mechanisms in superconductors, or really pushing the limits of how collective quantum states can emerge. But I kind of just want to have this slide to make the point that, in the far future, not the next decade, but much later, it might actually enable completely new applications. And I think that's, why this research is actually important. I leave it at that. Lots of people to be thankful to. This is like the most recent edition of my research group, including the two smallest members of the group. I have a lot of collaborators here. I only call out the ones that actually, whose work I talked about. And then, of course, I also want to thank all the places where funding is coming from. I might leave it at that. And maybe I flick back to this slide because it kind of like gives a nice overview of the nuggets that I gave. All right, I'll leave it at that.
Thank you very much,
so much,
Professor Nowack. That was a wonderful talk. Lots of exciting stuff. There's one question from Ayan Islam, who's asking, what is your opinion on research in room temperature superconductors, and will your research benefit from it?
I see. Okay, so what is my opinion? It's like, there's a few things to unpack. I've not been super involved with this. Some colleagues at Cornell actually have been much more involved with this more recent controversy, right? There was like a raging controversy about the discovery of room temperature superconductivity. My understanding is that it's really that there was some fraud involved, that there's I think all the papers have been retracted at this point, and so I think I don't think we have a room temperature superconductor at this point. But I think it's a very exciting direction, first of all. Also, like going into like the more curiosity-driven statement, like can we actually make something like this, right? There's another question, and I'm kind of optimistic that somebody, at some point, will make a room temperature superconductor. I think there's no fundamental reason why this is not possible. There's another nuance to this. Will it be a useful one? They are more doubtful, right? Like there's certainly materials that are like if it's, for instance, a high pressure superconductor, that's difficult. And then even if that's not the case, like sometimes, yeah, you have to think about if the materials that go in there are actually sustainable or like, easy to get, easy to make. And then there's even more nuances to it. Even if you can make it, can it support high enough currents to be useful for something? I think the interest in high temperature superconductors is, or room temperature superconductors would be mainly for instance, things like power transmission lines, things like that, right? That would be beautiful. But then for that to work, you actually also need to be able to carry high enough currents. Some superconductors, there's a limit of how much current you can push through a superconductor before it goes normal. So those are all, things. Useful to my research, I'm not so sure because I am really a low temperature person. I really am most excited about like really interesting phenomena where electrons behave collectively. And it turns out that low temperature is a friendly environment for that. Because if you're not at low temperatures, there's too much else going on in your material. So for instance, your whole lattice is in motion at high temperatures, right? Like there's lots of vibrations, lattice vibrations, and you really need to quiet those vibrations down to get to have the electrons take center stage, I think. Yeah.
Okay, very good. There's a question from Rainer Schicker, who asks, you mentioned that magnetic dipole moments can be measured with squids. Are such measurements sensitive to the anomalous magnetic moment of the electron?
Okay, let's see. Yes, you can detect magnetic moments. It's a bit of a so for my type of squid, there's a sensitivity question, like how small is the magnetic moment that we can detect with the like if I have an individual magnetic moment right now, because my squid is relatively large, I'm not that sensitive to that. So I like there's a single electron spin cares about one Bohr magneton, and I think I have a sensitivity maybe of 1,000 to 10,000 Bohr magnetons. There's other types of squids. There's a few different types of scanning squid centers. There's one type that gets a lot smaller, and turns out for magnetic moments, you actually become more sensitive if you make it smaller, and that has something to do with that the field lines for a magnetic dipole close on itself, and if you have a big loop, essentially all the field lines from that magnetic dipole actually close within the loop, and then you get a small net signal. So there are squids that have single electron spin sensitivity in principle. And there's also magnetic sensors like nitrogen vacancy centers in diamond that might achieve that too. And then if you say anomalous moment, we sometimes call this, I think, the orbital moment. And I would say yes, there's actually imaging experience. So of a single electron, I'm not quite sure how you, like it's a bit of a question how to do that, but there is imaging done on magnetic systems where the magnetization does not come from magnetic moment, like from actual magnetic spin moments, but from the orbital magnetization of electrons. So I think I would say yes. So orbital magnetism is a thing and has been imaged.
Yeah. Yeah. Okay, very good. So there's a question from Austin Nelson, who writes, I presume a squid is a continuous field monitoring device, but is there a limit to how rapid of a change in, say, the magnetic flux through the circuit can be detected, or is that bottleneck not with the squid itself?
I see. So for us, right now, it's not with the squid itself. So, and that has something to do also how we run the squids. So we actually increase the current slightly above their critical current. So we do what they call like a DC readout. And then we also have like feedback coils and whatnot. We run them in what's called a flux locked loop. Um, and it turns out that I think our bandwidth limit is much more in that feedback electronics at the moment. So we can achieve a little bit higher bandwidth in our measurements if we don't use the feedback and just like run what we call open loop. And there, if we do that, I think our limit is still in the wiring. Right now, we just have like really long, let's say 2 meter long twisted pairs of phosphor bonds going down to our squid. There's a lot of like some resistance and also straight capacitance in the lines that ultimately limit the bandwidth. Josephson circuits by themselves can be extremely fast. So there's other versions of squids that have been built, both using more like a microwave signals to read them out, and so they can achieve maybe a bandwidth of like 100 megahertz. What is that in time? 1 megahertz is a microsecond, so maybe 10, 20 nanosecond time resolution. And then you can even go beyond that with like, there's been sampling circuits. So there's a lot more specialized circuits that have been built to detect even faster signals if you want. So generally, I think Josephson circuits can be extremely fast. Of course, there's also always a question how big the signal is. To detect a tiny signal that's really fast is a lot harder than to detect a really large signal that's very fast. So yeah.
Mm-hmm. Very good.
But these sampling circuits that I just mentioned, they can only look at highly repetitive signals, but they have shown like I think 40 picosecond time resolution or something like that. Yeah.
Okay, there's a question from Khalid Keshk who asks, how do you apply a magnetic field to your thin film 200 by 200 superconductor? How do you measure the minimum field or critical current density required to introduce vortices in your film? And how do you image the vortices flow in real time?
I see. So there's a few things to unpack. One is we have images right here. So these, if you look at the length scales, like these strips. So here you look at superconducting strips. So there's no superconductor here, there's no here, but then the darker areas are superconducting strips, and the little blips are actually vortices hanging out there. The strip is maybe, in this case, it's probably close to, what is that? Is that a 20? Well, maybe that's a 40 micrometer strip, and this is the 20, this is 10. The way we take these images are, we have actually a big coil around our cryostat that can apply magnetic fields, but just not very high fields. So we apply on the order of like maybe 200 microtesla. Keep in mind, even Earth magnetic field is like 50 microtesla, about, depends on where you live, but that's the order. And so if you just do nothing and cool down a superconducting thin film, you have a lot of vortices in that film already. Actually, it's the opposite. We typically first need to screen our systems so that we don't get too many vortices. And then we have an additional coil to actually apply a little bit of field. Or we compensate the Earth field and whatnot. But so the field scale in this kind of image is maybe, I would guess, like 40 microtesla or so. And so that we just apply with a very large solenoid. When you think about the movie that I showed you of the vortices wiggling, I didn't carefully explain how that was taken. This is actually not like really a movie that we take, but it's like an image series of about, I think it was 25 images. And we literally take an image, then we warm up the film above the critical temperature, then we cool back down and trap vortices again, and they're just like, some get trapped in the same places, some choose to go in other places, and then we repeat that. And then we take an image, and then we warm up again, we cool down again, take an image. And I've just made a movie out of that image series. So taking that image series took probably 4 hours or something like this. And I just like compiled a little GIF out of those image series. We can't really, like our technique is not that fast. Like if you look at an image like this, it takes about at least 10 minutes, maybe 5, if we push it, maybe 5 minutes to take, but it's not a super fast technique. Yeah.
Okay, there are a few more questions, but in the interest of time, I think we will stop the public part of the webinar at this point and invite people to join privately if they want to ask questions further. But I would like to thank Professor Nowack for a wonderful talk and answering all these questions on very exciting physics. So thank you everybody for joining.